So before we start, any questions, any burning issues? So the deadline for the first, assignment is this evening, let's say before midnight. I know it probably says 5 o'clock or something like that. Let's do midnight. So, I'm not a deadline person. It doesn't really matter, but I know if I don't tell you to do it by a certain time, you won't do it. So, it's, let's say midnight. And I don't want much, as I mentioned to a couple of you already, bullets, just so I can tell that you're on track, right? You have a question, you have the data, you have the variables, and you have some sense as to how they will relate, and that's all I want. And then the next step is going to be you actually getting your data in place and do some initial analysis. And that's going to have to wait until we cover the specification tests, and so I may have to adjust the deadline for that. But the way I communicate is through Canvas, so the assignments will be put on Canvas. You submit them through Canvas. I'm assuming there's no problems with that. I know Canvas is new for you. I've used it for a couple of years at another university, and I prefer it greatly over Chalk, which is Blackboard, and Blackboard I don't like. So what I'm going to do today, as I mentioned on Monday, is continue the kind of generic discussion of spatial process models. And what we did on Monday was talk about the actual problem of modeling covariance with a spatial structure. So the question then is, how do we get the spatial structure into the covariance? Because without that is just covariance that is non-spherical. So you have non-diagonal elements that are non-zero, and that's it. But how do we get the structure? We saw there's 3 major ways of doing this. One is fully functional. You put in a distance decay function with a parameter, you estimate that parameter. Second is kind of the same flavor, but now rather than putting in a fully specified function, it's non-parametric. So you use something like a kernel or a spline function or a polynomial to fit the covariance strength and then figure out the range of interaction and things of that nature. Both of these approaches have 2 things to keep in mind. One is that, especially with the non-parametric one, you might violate Tobler's law in that at some point in the distance range, covariance may actually increase with increasing distance. And the general rule is that it decreases with increasing distance. You'll never have that problem if you pick the right functional form, because the functional form will ensure that this happens. The second problem is a little trickier, is that you have to ensure that the resulting variance-covariance matrix is positive definite. And that puts constraints on the parameters of the model. So it constrains your parameter space in the case of what we call direct representation, where you have the function, but then in the non-parametric case, you don't exactly control that. So you have to check whether whatever comes out of your non-parametric fit actually makes sense in terms of the positive definite nature of the resulting variance matrix. And then we get into the more interesting part and the more commonly used part, which is where we actually specify a spatial stochastic process, which is a model that specifies how a random variable at one location is related to random variables at other locations. And out of that functional specification follows a structure for the covariance. So the covariance, to put it in concrete terms, in your specification you use a weights matrix, a spatial weights matrix, which we covered before. The covariance does not match that weights matrix. The covariance is whatever follows from the specification of your model. And we saw, for example, in a spatial autoregressive specification, that the resulting covariance, even with a very sparse weights matrix, is a dense matrix, where everything is correlated with everything else, right? The other thing we saw, which is very weird, is that the diagonal elements of that variance-covariance matrix were no longer constant. Even though we start with a process that has a constant variance. After we put it through the spatial process, we end up with a variance that is not constant, and that is due solely to the structure of the weights. So as we saw, if we have non-constant number of weights by observation, of non-zero weights by observation, then we end up with this weird heteroscedasticity, which of course in practice creates problems for specification testing because you don't know whether the heteroscedasticity that you find is for real or is a result of your spatial process. Right? And we made a distinction between simultaneous processes and conditional processes. So simultaneous processes are models for the whole full pattern, everything. Right? Conditional processes are best specified in the context of spatial prediction. So you have observations at given locations, and you use those to predict values at locations that you do not observe. That is the classic case. But in statistical theory and practice, this same way of thinking about things is also used in Bayesian models to specify priors for Bayesian parameters. And that is what I'm going to be talking about mostly today, even though we don't really cover Bayesian analysis in this class. That's a whole class in its own right, or a couple of classes. I do want you to be aware of these concepts because these are concepts that you see in the literature. You see in the papers, especially in the statistical literature. The Bayesian approach is by far the dominant approach, especially for models that do not deal with continuous dependent variables. So if you have things like binary 0, 1, or multinomial categories, or counts, where you have non-standard models like, multinomial models or count regression models, then it's very hard to deal with that explicitly in a spatial autoregressive framework, and I'll talk about why that is the case. But in a Bayesian hierarchical framework, which is essentially a random effects modeling framework, where you make either the parameters or the parameters plus some random effect part of the model, and then these random effects or these parameters have themselves parameters, and that's where the notion of hierarchy comes on, parameters of parameters of parameters. That's where the conditional models are used a lot today. So first, as before, we start with some time series, just to make, again, illustrate how different spatial processes are from the time series domain. So in the time series, there is, and it's all about connecting conditional distributions to joint distributions. So the ultimate goal is always, and you can't get away from this, to have a joint distribution, which means for all the random variables together. So in our context, that would be a joint distribution for all the y values, which we've been calling the dependent variable, y values at all the locations, right? What is the joint probability of this? What is the mean? What is the variance? What is the covariance? Can we condition the conditional mean on some variables, like in a linear regression, et cetera, right? But the conditional distribution is when you control part of the story. And for example, in time series, it's very easy to think about controlling for the past, right? And you can actually show formally that any joint probability density or probability distribution can be factored out in conditional pieces. So if you have, say, a time series from y1 through yt, you can start with t, let's say that's today, conditional on everything in the past. And then you do yesterday conditional on everything in the past. Okay, I'm still standing. And then you keep going to the past until you end up with the starting point, which is point 1, time 1, right? So you have the probability of point 1. Then you do the probability of point 2 given what you saw yesterday. Then point 3 given what you saw at 2 and 1, and so on, right? And that is very standard. That's two completely equivalent ways of representing the total stochastic properties of, if you can call it that, the landscape, all the y's that you observe, right? So that's pretty standard. And this is complicated. So in time series, as you probably know, there is a property called the Markov property, which says, you know, if you, let's say you want to know something about today's temperature, all you need to know is yesterday's temperature. You don't really need to know what happened the day before or the day before that or last year. So that's the Markov property. It's kind of an instantaneous neighbor property. So the conditional probability, let's just call it probability, of today given the whole past, the whole history, is actually the same as the conditional probability of today given yesterday. So all this other stuff doesn't matter. Which of course then really simplifies the factorization that we have here. And we just have a product of conditional probabilities that relate t to t minus 1. And we do this all the way till we end up at the very beginning, because we can't get around that, right? So we can build up the whole history of the process by just knowing what happened one period previously, right? That's a very powerful thing, because it allows us to, typically these conditional probabilities are simpler than the full joint probability. And, you know, in this case, they could be univariate, right? And so you get a, you know, say you have a history of 1,000 observations, rather than dealing with this 1,000 by 1,000 monster, you deal with one time at a time, conditional just on the day before, just on the period before, which is very powerful, right? So if you know, let's say this conditional probability has a fixed form. We call this a transition probability in the Markov world. So if you know how you move from one day to the next, if this is constant, then you can very easily build up the whole joint distribution just with these very simple conditional probabilities. So this is very powerful, right? We want to do this in space as well, because in space we have the same thing. We have a joint distribution of everything at every location. How can we factor this out? Since this is a general property, we can factor it out. But unlike time, where we know, you know, the past is before now, in space there is no such ordering. We saw that when we talked about the spatial weights. Everything depends on everything else, closer things more so, right? So even though conceptually you can write the joint probability as a product of conditional probabilities, one for each location, conditioned on all the other observations in the data set, in the landscape, if you wish, that's really hard to do uniquely. And it's very easy to do wrongly. So if you just set up some conditional probabilities, that doesn't mean that when you multiply them through, that you end up with something that makes sense. Okay? And what does making sense mean more formally? It means that the resulting probabilities have to be between 0 and 1. And if you combine them all, you cannot be over 1. And obviously you can't have negative ones, which is unlikely. But that is something that is not obvious. And if I had more time, I would give you some actual numerical examples of when this does not work. You can't just set this up. In fact, if you go to some standard econometric textbooks and you look at the treatment of the multivariate normal distribution. So multivariate normal distribution has this sigma variance covariance matrix, right? And let's say you have a 3x3 setup. You can express the conditional, you can express the marginal distribution of a multivariate normal that's also normal, And then you can also express the conditional distribution. Say if you have 3 variables, you do probability of 1, variable 1, given 2 and 3. And you can get that proper form of that distribution from subsetting the variance-covariance matrix, right? It's very specific what the terms of that conditional distribution will be, which means you can't just put anything. It has to be exactly that combination of covariances from the full variance-covariance matrix. And just think about that in space as well as the same thing. You can't just put anything. The variance-covariance matrix for each of these conditional distributions has to be compatible with the pieces of the full variance-covariance matrix. So you just can't just put numbers in there. They all have to fit together. So basically, you have to partition the full variance-covariance matrix into pieces that match. So it's not simple to do. It's not unique. There's multiple ways in which you can do this. And if you just do it like that, it doesn't necessarily work. In other words, if you would just estimate a bunch of these conditionals, that doesn't mean that the joint distribution that corresponds to it necessarily makes sense. In other words, the means and the variances and the covariances that you get from these conditionals don't necessarily match up to a full variance-covariance matrix that makes sense. For example, is positive definite, right? So that's the main problem. So to get around that, there is a whole very difficult mathematical statistics literature. And I don't want you to necessarily delve into this, but I want you to know the terms, because you see these terms, right? And there's a progression of terms that we use to get around this problem and to give us the rules that we need to follow to build conditionals that get us the joint distribution. Now, just running ahead, those of you who's done any Bayesian analysis? Okay. So have you heard of Gibbs sampling? Markov chain Monte Carlo sampling? So what's the idea? The idea is you sample from very simple conditional distributions, and if you set it up right, the result is a sample of the joint distribution. So you go from the conditionals to the joint, right? How can we do this in space? That's the challenge. And so there are a number of these mathematical pieces. One is called Brooks' lemma, and Brooks' lemma is really very complicated, and it doesn't help that the text that I copied this from actually has a typo, but the typo is here. This should be n, not 2. So, but you see what's going on. Basically, we are anchoring all these conditionals to a joint distribution of a given location, 0, an anchor point. So if we have this anchor point, then we can have proportions of conditional distribution. So it gets really complicated, right? If you look at this very carefully, what we have at the very bottom, we have our anchor point, right? The joint density at point 0. And then we have a bunch of relative proportions of conditionals. Conditionals basically building up from one element of the anchor point and gradually adding more and more elements of the anchor point. So you see the first one is conditional y1, conditional upon everything else in y. And in the denominator, we have the anchor point conditional on everything else. Okay. So then the second one is y2 relative to y2 on the anchor point, but one of the conditions is now the y1 at the anchor point. And so it keeps building out until you hear the next to last one, everything at the anchor point is in the condition, right? This, I mean, if you're with me, may sound nice. Just think of it as a mathematical trick. It's a mathematical trick of getting around this problem of the non-uniqueness of the conditionals to get the joint. Because you need to get the joint from a product of conditionals. This doesn't quite do the trick, but it gives you ratios of these conditionals. Now, these things are very complicated because they all condition on everything else, right? Just what I like to do is when you think of these things, think of 3,000 counties in the US. So for each county in turn, you condition on 2,999 counties, right? You pick one in particular, say Cook County, that's your zero, that's your pivot. And then everything else is conditional upon what you see in Cook County. And so it's really kind of a hard way to think about this. So mathematical statisticians being who they are, they make things simpler, right? So they come up with this concept of a Markov random field, which is probably a term that you will see the most in the literature. It's the counterpart of a Markov property in time series. But in time series, it's very simple. It's a previous time point. In space, it's not that simple. So basically what we're doing with a Markov random field is constraining who we condition on. So just like in time series where we condition just on the previous time, now we're going to condition on quote-unquote neighbors. Okay, so what are the neighbors? Right? And this is where it gets a little complicated because the formal requirements to make this work really limit the structure of the neighbors. And this, if you're going to remember anything from this lecture, is that conditional models have severe constraints on the neighbors, on the weights, basically. Right? So in a Markov random field, we say rather than, like before, one location conditional on all the other ones, we do one location conditioned on a few. Okay? And that's the Markov random field. So as I said, these Brooks lemma conditionals, they're a pain in the neck. I don't know of anybody who actually uses this other than in theoretical proofs. But the Markov random field is used all the time. So you have to set up what are the neighbors, and then you have to set up under which conditions does this actually work, right? Under which conditions do we go from a local specification, which is the conditional one, the Markov random field. So, for example, that is, you know, the variable is normally distributed as a function, and the average is a function of the averages of the neighbors, and then there's a variance term, right? So for each location, there's an average of the neighbors and a variance term. How do you make this work? So that the end result is a proper joint distribution for the variable at all the locations, right? And as we'll see, with normal distributions, this actually works fairly well. When you are not in a normal distribution case, it becomes very complicated, right? So what are the rules? And here's this very famous theorem, which actually was never proven. It's only till very recently that there are some formal proofs of this. But this theorem is called the Hammersley Clifford theorem, and it was actually a working paper that circulated. And it was pretty critical because it established the formal connection between the Markov random field setup and a proper joint distribution. And there's some more lingo here. So to have these set of conditionals that are Markov random fields correspond with a proper joint distribution, that joint distribution can only be from a given type, and it's called a Gibbs distribution. And this comes out of particle physics, where that's where the origins of these models come from, where you have, you know, I'm not a physicist, so I don't really know how this works, but apparently something's spinning around something else, and you have to figure out how this all fits together, right? So you have a model for the thing and what spins around it, but you're actually dealing with a whole universe of all these things spinning together, so that has to make sense. So this Gibbs distribution is a particular animal of a very restricted sort, as we'll see in a few minutes, right? And this is actually where Gibbs sampling comes from. So the Hammersley Clifford theorem established a proper connection between the conditionals and the joint. So in Gibbs sampling, we actually flip it around, and we use the conditionals. We sample from the conditionals to get a distribution that gives you the joint distribution. So you set up a bunch of samplers, which typically are very simple conditional distributions. Classic example that I use in my classes, bivariate normal distribution. So how do you sample from a bivariate normal distribution? So bivariate, you know, is a variance, 2 by 2 variance matrix. You can all write this down, this equation. So now we write down the equation for the y1 conditional on y2, and that happens to be a normal distribution with a mean and a given variance. And then y2 conditional on y1, and that's also a normal distribution with a mean and a given variance. So how do you do this? Given this variance, you sample, say, y2. You start with something for y1, random. Then you sample y2 given y1 from that distribution. So then you plug y2 into the next one and sample y1 given y2. And then you keep doing this and flipping them back and forth. And after a while, this whole thing stabilizes. And then if you take y1 and y2 together, they're actually samples from the bivariate normal distribution. And the reason this works is Hammersley Clifford, because it just shows you under which conditions these conditionals build up to the proper joint distribution. So these Gibbs distributions are actually very limited, okay? And they have two things that we'll have trouble formalizing when we deal with weights later. So one is this notion of a clique. And a clique is basically a group of people who talk to each other but don't talk to anybody else. It's not people. It's random variables that are correlated or covary together but not with others. So you have to set this up. And so a simple clique is just a pair. You have pair, 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 or triangles. And once you get beyond that, it gets much more complicated. So that's why you never see these. Most of the discussion, most of the literature, most of the textbooks deal with functions that are either cross products or square differences, because these are easy. They're exchangeable in the sense you flip yi and yj and it's the same product, right? So it doesn't change. So then, you know, we can dwell on this. They have a particular form for the exponential family of distributions. This is well behaved, so the normal is one of them. So the thing to remember is that these Gibbs distributions are very particular. They are of a very restrictive form. And as long as you play by the rules, then you can go up and you can go down. So you have the joint factors out into conditionals, and the conditionals multiply together to a proper joint. It's a long story. So what does this mean at the end of the day? The Hammersley Clifford theorem dictates particular functional forms for the conditional models to ensure that when you throw all the conditional models together, you have a proper joint distribution. Remember before, when we talked about the simultaneous models, we worked directly with the joint distribution. We didn't talk about conditionals. So we did the full joint distribution, this variance covariance matrix, you know, remember the I minus rho W prime I minus rho W inverted. That is for the whole thing, right? Here we're going to work with one observation conditional on its neighbors and then build up from there to the joint. So what it means, you have these kind of models are called auto models, and they're all conditional. And you should know that because sometimes, you know, well, every year there are some people in the class who want to do bivariate dependent variables, 0, 1. And they want to do some kind of a logit. And they might have seen in the literature this thing called an auto-logit model, which is a spatial model. Well, it is, but it's a conditional model. And that means you can't just do anything. For one, your weights have to be symmetric. And so far, our weights have tended to be row standardized, and there's good reasons for that, as I talked about a couple of weeks ago. Row standardized weights are not symmetric. So forget it. And as I mentioned the other day, why is that important? Because the parameters are really what we're modeling is the product of the two, the product of the weights and the parameter. So if these weights are different, then the parameters are going to be different. So that makes it very difficult to compare the parameters of conditional models because they are a function of what is in the weights. Whereas when we row standardize, as we'll do in the regression models that we'll talk about next week, these parameters are actually comparable. So if you have 0.5 and 0.7, you can say 0.7 is larger than 0.5. You know, with the conditional models, you can't necessarily say that because it all depends on what's in the weights, right? So this Hammersley Clifford gives you a family of distributions that you can actually use for this. And the catch, and this is really hard to get an intuition for, is that only when you work with normal distributions are they all of the same family. So, you know, you have a multivariate. If it's normal, the marginal is normal, the conditional is normal. They're all of the same family. With other types of distributions, that's not the case. For example, if your conditional distribution is, let's say, a Poisson distribution for counts, then the multivariate, the joint distribution, is very complicated and typically not a Poisson distribution. So that's something that is very, in some sense, counterintuitive because you're modeling something, and the way you model it between the joint approach and the conditional approach is different. Again, in a normal distribution world, you don't have to worry about this because you can go back and forth and it's all the same. It's all a normal distribution. Once you get out of that, so once you get in the logit world, or you get in the Poisson world, or the binomial world, negative binomial, forget it. So then it's very difficult conceptually to think about what it is that you are modeling. I talked about that last time, where it's so difficult to, when you write down a specification, to not think of it as conditional. So we write an autoregressive model, and we say the prices of a house are a function of the prices of neighboring houses. That's conditional thinking. That's not what we're actually doing. We're modeling all the house prices through this spatial process. In a conditional world, you know, you can say this. And then the question is, what is the joint distribution of all the house prices once we get set up these conditionals, right? And again, in a normal world, you can make the connection between the two, but in a non-normal world, and I know it's not modern to use that term, so Gaussian and not non-Gaussian, you know, you're in trouble, basically. And you'll see, and if I get to it, you'll see what kind of a trouble you get into. And you get into trouble in the terms of constraints on the parameter space. You know, for example, in a Poisson, auto-Poisson model for counts, can only model negative spatial autocorrelation. And most of us are interested in clustering, which is positive spatial autocorrelation. Negative spatial autocorrelation, if you remember, is this checkerboard thing. You know, it's high degree of heterogeneity. And that, you know, is typically not what we want. So forget auto-Poisson. You can't, I mean, I'm exaggerating. I mean, it's interesting in its own right, but for most empirical problems, it puts restrictions on the parameter space that are not compatible with what it is you're trying to model. So you have to keep that in mind before you just pull some, you know, package out of R and start fitting it to your data, because these packages are out there, right? Okay, so what are these models? And it's very confusing, right? I'm the first to admit that. my rule of thumb is simultaneous models the pattern. Conditional is one at a time. And you hope that by combining them, you get something for the pattern that makes sense, right? And we'll see in a few minutes that from a Bayesian point of view, that's just fine, because you're not actually modeling real data. You're modeling parameters of a model for real data. So you're kind of like one step removed. So if, for example, let me just give an example before we get into the math. So if you say, I'm going to model house prices, and I'm going to put together an autoregressive model, right? So you're actually modeling the house prices. Instead, if you say, okay, I'm modeling the house price as a function of the house characteristics, which is a parameter, let's call it beta. But beta isn't fixed. Beta is random, and beta is different for each observation. Now, you can't really model that because that's the incidental parameter problem. You have one parameter for each observation, you're out of luck, right? But now we put some structure on this, and the classic structure in random coefficients model is say, okay, let's say this beta is normally distributed with some mean beta bar, the average beta, and some variance, right? But now if we want to be really clever, we say, well, beta is actually spatially correlated in that the betas of neighboring houses are going to be similar. So how do we put that structure in there? We put that structure in there through a model for the spatial process of the beta. It's not data, it's just some random factor. And that is then where the conditional setup comes into play. As long as you set it up that the ultimate joint distribution of the betas is fine, you can set up a conditional setup. So you can set up a model where you say, okay, the beta coefficient for the garage, the implicit price of the garage, depends on the implicit price of my neighbor's garages. And just me conditional on my neighbors. And if you set it up properly using these Hammersley Clifford rules, and we'll see some examples of this later, then that actually results in a joint distribution of all the betas for all the houses that is proper, right? So you don't have to think about it as an actual distribution for the prices, but it's a distribution for the parameters that determine the prices. So it's one step removed. So the first model is a formal model for what is called a normal Markov random field, and is actually just something that is of theoretical meaning because it's not very practical. But just to show you the kind of constraints that are involved in this. So this specifies directly the conditional distribution of y at I as a function of the other locations, all the other locations. You'll see in a second where the constraints come in, as a weighted average of the values at the other locations. We've seen this before. We've seen this in, say, the Moran's I coefficient. We have this sum over wij, yj. That's what this is. We call it bij here. And then we have heteroscedasticity. So right off the bat, you should know, I'm not going there, right? Because if you have a difference variance term for each observation, I'm never going to be able to estimate this. This is why this is not, as I said, a very practical model. It's more of a conceptual model. Because it tells you the kinds of, so this model is fine, and with some hocus pocus in algebra, you can show that its joint density, so the joint density that you build up from all these conditional ones, takes this particular form. So D inverse is a diagonal matrix with the inverse of the variance terms on it. I is your identity matrix, and B is the matrix of all the Bij coefficients. Now, you know, or if you don't, you should, that the variance-covariance matrix of a multivariate distribution has to be symmetric, right? And as such, there's nothing that guarantees that this term is symmetric unless you constrain it in such a way that this holds. So Bij over the variance of I has to equal Bji, its symmetric element, over the variance of j, which puts constraints on what this B and what these variances can be. The other thing is that this is nice and normal, and if you really focused on this, you would notice that there's no squiggly n there, right? All it says, it's proportional to this exponential term. So here, you have a very explicit constant of proportionality. Basically, what you need this for is that, so for continuous variables, you have to take an integral to make sure that everything sums to 1, so to speak, right? But this doesn't do this. This piece is missing. So this sums to whatever it is, and then you divide it by a factor to make sure that that is 1. So it's proportional up to a constant of proportionality. And in a lot of practical manipulations, even in Bayesian Markov chain Monte Carlo simulation, you don't have to worry about this constant. So you can, as long as you know that it's proportional to something that's well behaved, you're in business. So this is good to think about. You know, in a way, it's a reality check. It tells you, hey, I can't just do this. I can't just put any b's in there or any sigma squares. This has to hold, right? So now we all know about spatial weights. Now we're going to put in spatial weights. And this is called, and I've always found this very confusing, so I'm not expecting you to get it right away, so to speak. But this is very confusing because this is actually a model that is not a proper density. So it doesn't sum to 1, right? But it is used in a lot of Bayesian modeling as a trick, you know, because it doesn't have any parameters. So we have our weights. We put in the neighbors. So rather than Bij, which are all these possible values that we then put constraints on, we have the weights, and then we row standardize the weights. So you see it's a normal distribution, the sum over the Wij Yj divided by Wi plus, which is the sum of the row elements. So whether you write this like this or you do Wij divided by Wi plus is the same thing. These are row standardized weights. So there's row standardized weights, but then the variances are connected to a common variance divided by the sum of the row weights. So now we're a little bit more in business. Rather than having this tau squared I, a different one for each observation, now we have 1 tau squared. It's still heteroscedastic because you divide it by a different number, a different row weight sometimes, right? The Wi plus is the number of neighbors. The Wij is 0, 1. So if you divide 0, 1 by the number of neighbors, you get a row standardized weight. And the thing is that this is not right. Why is it not right? Because we have this d minus w as the variance covariance term, and there's a problem with it. Because of the way that we define the weights, this matrix is not invertible. It's singular. And why is it singular? Because the row weights sum to 1. When they're standardized, they all sum to 1. So W as a matrix cannot be inverted. It's a singular matrix. So why would anybody do this? You know, you end up with a distribution that doesn't have a variance. I mean, it sort of does, but it doesn't have an inverse variance. Actually, this is the inverse variance. So the variance doesn't exist. The inverse exists, right? That's kind of the mind trick that you have to do. And in the Bayesian literature, it's often advantageous to work with the inverse variance rather than with the variance itself. And this is one instance. So the inverse variance, because in a normal distribution, it's y prime sigma inverse y, right? So this part in the middle is sigma inverse. So you have sigma inverse, but you don't have sigma, because sigma is the inverse of this. So the actual variance-covariance matrix doesn't exist. But this, of course, as an algebraic expression, does exist. So you can use this in a sampling scheme. And this is used in some, as a prior distribution for parameters that show spatial autoregressive behavior, spatial clustering, right? So this is actually what you use in the sampling. This is the conditional distribution that you sample from. And this is the joint that corresponds to that, but there's a problem here with this joint. It's improper, right? But you don't actually care. That's the bottom line, right? I mean, this is not a proper distribution in the strict sense, but for the mathematical purposes of sampling a conditional distribution, it serves some purposes. So this is where we get off into the Bayesian world. Typically, this is done if you center the variables. So you make everything in deviations from the mean, and then you can do the sampling. But anyway, this is a term you will see in the literature, intrinsic autoregressive model for conditional spatial processes. What it means, in essence, is this is a model for priors in a Bayesian analysis. It's not a model for a proper distribution because the distribution doesn't have a variance, right? So in other words, it sort of doesn't exist, right? But it's good enough for as a prior distribution because then you can sample from it, and you can sample from a normal distribution very easily. That's one of the easiest ones to know. Okay. So now we're finally with a model that actually works. So that's a proper CAR model, conditional autoregressive. And the big difference between the intrinsic autoregressive and the proper one, it's kind of subtle, and you might not have noticed it, is this rho. So now we have a parameter here. So it's no longer singular. It doesn't sum to 1 anymore because we scale it by this rho, and rho is less than 1. So now the whole thing is invertible, because instead of d minus w, which is not invertible, we have d minus rho w, which is invertible. Right? So now we're in business. And this is the actual conditional autoregressive model that is used in a lot of Bayesian hierarchical modeling. And you see it has two parameters. It has a variance parameter, and it has an autoregressive parameter. So in Bayesian modeling, you have to specify priors for these. And that's tricky business, right? But there is a large literature on how to do this, you know. So rather than what we will be saying in the traditional world, saying our parameter space, for example, for the autoregressive parameter, is bounded by 1 over the smallest and the largest eigenvalue of the weights matrix. That's the bounds, right? Here we go much further than that, and we have to say, okay, the prior is a uniform distribution between those bounds, right? But uniform is actually maybe not that good because it gives equal probability to very negative and very positive autoregressive coefficients, which basically in practice you don't see. So then you want to put a little bit of centering, maybe around 0 in that. And so that's where the literature has multiple alternatives for priors of the spatial distribution. But that's how it works. So then you can sample because you have this normal distribution, and you know that it has a proper joint distribution at the end of the day. So you can think of this as a regression model also, but it's not used that much. So conditional upon the neighbors only, that's this spatially lagged term there, and the major thing is that the variance-covariance matrix of the joint distribution is sigma squared times I minus lambda W inverse. So the big difference with what we had before we had an inverse of a product of a matrix transpose times a matrix. That is always symmetric. You know, A prime A is always symmetric. That's just basic matrix algebra. But A by itself is not necessarily symmetric. So the only way you're going to get this matrix to be symmetric is if W is symmetric. And we just talked about row standardization, so you cannot have row standardization in these kind of models. So the parameters will have very different magnitudes from what you see in simultaneous models. Even though you may be modeling the same thing, it is not the same thing. And I'll show you with my usual examples that it's not the same thing. So one thing is you can always represent a simultaneous model as a conditional model, because the variance of the conditional model is this y minus, you know, we saw the rho w, right, or the lambda w. So for a SAR model, it's really more complicated. So if we make this part equal to c, we have a counterpart representation of the same process, but as a conditional one. But it's not the same, right? It's not W anymore. It's this combination of W, W prime, and W prime W. So that's a different animal. So they're not the same. It's just like moving average and autoregressive. It's not that one is better than the other. They're just not the same. And here it gets very confusing because they're both called autoregressive. So simultaneous spatial, or sometimes people think spatial autoregressive is this, right? So that's why you always have to specify it's either a simultaneous spatial autoregressive model or it's a conditional spatial autoregressive model. They're not the same. And I have my usual little numerical example where I just use the same scheme as the other day with the 6 units, and we plug in the numbers and we get the 2 variance-covariance matrices. So takeaway points. First of all, you don't get around the heteroscedasticity problem. It's the same for both. Okay? And this complicates matters to some extent, right? Then the second thing is that all the variances in the CAR model are smaller than the variances in the simultaneous model, everything else being the same. So you might say, well, you just said that the parameters are not the same. Well, that's exactly what I'm saying. To get the same variance structure, you need a different parameter value in the CAR model, right? So here I plugged in 0.2 for both. So we end up with different covariance structures. So these two models are not the same. Even though they look the same, they have the same parameters, they model a different type of covariance. And again, I'm not saying one is better than the other, but you should know that a CAR model has much weaker covariance than a SAR model. So in each empirical situation, you have to assess that, whether that is appropriate or not, right? The thing to know that there's less, everything else being the same, there's less spatial dependence in a CAR model than in a SAR model. Both have the heteroscedasticity problem. Both have the problem that even though you start with a very sparse representation, you know, the Markov random field has only a few neighbors, very sparse, you end up with a dense variance-covariance matrix. Right. So that's kind of something you have to get used to, this disconnect between the specification of the model as you write it out and then the resulting variance-covariance structure, which typically is much more complicated. So just to summarize, same overall pattern. SAR variance is larger, covariance is larger, is a faster decay for the CAR model. The range is not as large. So everything else being the same parameters, same weights, SAR reflects a stronger parameter, just what I mentioned before. So now finally the auto models, and the auto models are these conditional models that take a form. This is where the auto thing comes in. So they are in general belonging to the exponential family, which if you don't know what this is, it's basically a mathematical specification of a whole range of different distributions, like the normal distribution, Poisson distribution, gamma distribution, beta distribution, are all members of the family of exponential distribution. And they're characterized by some mean function and some variance function. So, you know, as long as they are part of the exponential distribution, you can use Hammersley Clifford to make the connection between the conditional setup and a proper joint setup. So the general form of these is a conditional specification, and now y at I can be a continuous variable, or 0, 1, or multiple categories, or a count. You know, doesn't matter. It's all part of the exponential family. We have some regression part, a regressive part, which will typically allow you to have a varying mean, right? So it's all about a conditional expectation. So in a conditional expectation, we let the mean, a conditional distribution, I should say, we let the mean vary from observation to observation, but it varies as a function of specific variables x. And this is the linear regression specification, and this part is the auto part. So this is your weights and the observations on the dependent variable at adjoining locations. So this is the general form, and then the specific form depends on the distribution that you're working in. But remember, typically, the moment you leave the normal world, the Gaussian world, the joint distribution is not of the same family as the conditional distribution. So you start with Poisson for the conditional, the joint is not. You start with negative binomial, the joint is not. You start with logit, the joint is not, right? Which is different from your standard econometrics, where you work with the joint distribution, not with the conditionals, right? So for binaries, we have this autologistic or conditional spatial logit model, which is has seen some application. So it's kind of a little bit complicated, but in the end it's not, because the logit, so the proportion of the odds, the log odds, are a linear function of the usual explanatory variables, and then this autoregressive term. In a conditional model, the y in the condition is observed, is 0 or 1. So you observe the zeros and the ones, you stick them in there. As we'll see if we ever get to it, in, say, a latent spatial model like a spatial probit model, which is used to model zeros and ones, the zeros and ones are not observed on the right-hand side. But the latent variable, which is a continuous variable, is observed. So the way you think about these kind of models in a simultaneous world is you have a latent variable, they call it y star. You know, y star is the propensity to get sick, right? And then you do your sample and you have sick people and people who are not sick. And so the way you think about this, the sick people, the ones, are the ones where the propensity to get sick, y star, exceeded a certain threshold. And the zeros did not exceed this threshold. And now we make a spatial model for y star, not for y. Here we're making a spatial model for y directly. And the only way we can do this is through this conditional setup. The joint setup basically doesn't work, right? So this is autologistic. You might see this in the literature. And here's auto Poisson that I mentioned earlier. So you see the conditional probability is the usual Poisson expression with an intensity alpha I, and then alpha I is a function, log of alpha I is a linear function of x, and then the autoregressive counts. The tricky part with this is that we have to ensure that the result of this model are counts, right? So if you have a model for counts, 1, 2, 3, 4, 5, and your predicted value is 2.5, that's not what you want, right? So you want to keep the counts in there. So the way we finesse that, typically, is we don't model the counts, we model the intensity, which is the parameter of the Poisson distribution. So it's a Poisson distribution with mean 2.5. How many actual counts do I get? And they will always be counts. So that's kind of another step you have to make to keep track of this. But basically, this is where Hammersley Clifford comes to bite you, because the only way you can do this without further restrictions is to model negative spatial autocorrelation, which we're basically not interested in. So the best practice, if you wish, to model count variables this day and age is as a Bayesian hierarchical model, where you basically have this set up, but then this becomes a random parameter. So either you have this in this linear form, but rather than having this thing, you have a random factor, random effect in there, and then that random effect has a conditional autoregressive prior. And that's how you bring the spatial dependence into the model. So you don't model the spatial dependence of the counts directly, you model the spatial dependence of the intensity of the distribution through a random effect. That's the way it's done. So there's a little bit of a disconnect. Okay, so I know this is all, I know this is all overwhelming, because it was overwhelming to me when I started getting into this. But it's really important, before we get too used to clicking away or, downloading packages and running it, it's really important to at least conceptually know there's a big world out there, right? There's a big difference between simultaneous models and conditional models, at least in concept. Simultaneous models model the variable directly. And that's typically, at least as social scientists, what we tend to do, but it doesn't always work. And in those situations, we model the variable, the spatial patterns, indirectly through spatial patterns in the parameters of the model. And that's where the Bayesian approach comes in, and that's where these conditional models come in, because they provide a natural way to sampling, sampling from conditionals. You see these are normal distributions or very simple distributions with only a few factors on the condition part, so that's easy to do. Okay, so I'll stop a little earlier than usual. It wasn't as early as I thought it would be, but anyway, those of you who have questions, if you want to talk to me now, or give me 5 minutes and I'll go to my office, and then you can come there.